segment trees before? Well, you are in luck because today we are talking about segment trees. So in this video we will start by motivating the problem. That is to say, we will discuss why on earth would we need a segment tree for. Next, we will see the intuition behind segment trees, and we will build upon that intuition step by step until we reach the full-blown data structure. After that, we will reach our first milestone by implementing a segment tree. Our first implementation will not be perfect. It will not be memory efficient. That's why we will present a second implementation that is memory efficient. And finally, we will present a templated implementation that allows us to work with any data type. Afterwards, we will tackle updates, and by then you will be aware that segment trees allow for updates, both point update and range updates, and we will see how we can handle both types, especially by using lazy propagation. And finally, we will introduce other kinds of segment trees. We will see two-dimensional segment trees, implicit segment trees, persistent segment trees on trees, DP with segment trees with vectors, and a few other types of segment trees. So without further ado, let's get started. Consider the following array. It has length 8 and it is 0 indexed. Let's call it A. Each time I will give you two integers I and j between 0 and 7. And I will ask you to calculate the sum of all entries between I and j. Let's do an example. Let's calculate the sum of entries between 2 and 5. Originally, the sum is 0, and the number of additions we performed is 0 as well. So we'll start with 2. Then 3, then 4, and finally 5. So as you can see, the answer is 26 and we performed 4 additions to get to that answer. Now let's try another example. Let's calculate the sum of all entries between 0 and 7. So this time we will speed up the process a bit. So the answer this time is 37 and we needed 8 additions to get to the answer. From these two examples, it is not hard to see that the number of additions we will need will be equal to j minus I plus 1. And in terms of complexity, we can say that the number of additions is asymptotic to O of n, because in the worst case we would need to sum up the values of all entries in our array. And if we needed to answer Q such queries, the total number of additions would be of order O of Q times n. because we require O of n per query and we will have Q queries. So this first approach is not efficient at all. Let's try to find something better. Let's go back to our example. We can rewrite the sum from 2 to 5 of A of n as the sum from 0 to 5 of A of n minus the sum from 0 to 1 of A of n. Let's visually verify it. So the block in green is the sum from 2 to 5 of A of n. And this block in blue is actually the sum from 0 to 5 of A of n. And finally, the difference between the two blocks is this block in red, which is the sum from 0 to 1 of A of n. And in actuality, there is nothing special with the example we picked. We could apply this breakdown to any value of I and j. So the sum of values between I and j will be equal to the sum of values between 0 and j minus the sum of values between 0 and I minus 1. So our problem that seemed to depend on all possible combinations of I and j between 0 and n, which would be of order n squared, can be simplified or reduced to only the values from 0 to a given value between 0 and n. So we reduce the possibilities from n squared to n. So basically, if we know the value of all these sums from 0 to any index, then we can answer any query I and j. Now let's take a closer look to these values. So there are two important things we can notice here. First of all, these values we are interested in form the prefix of this array. So for any given index, the sum from 0 to that index will be actually the sum of the prefix that ends at that index. Moreover, to move from the sum up to I to the sum up to I plus 1, we simply add the value of A at I plus 1. That is to say, when we move from a prefix to the next prefix, we simply add the next value of the array at that position. So this observation will allow us to build all these sums in linear time. So the sum of the first prefix is actually equal to the value itself. So the first prefix will be equal to 4. And to get the next prefix, we simply add the last prefix to the value of A at index 1. And we get 6. Then we continue this way, we get 11, then 12, then 24, then 32, 34, and finally 37. So in code, it would look something like this. Suppose we are given an array A of ints, then we define an array of prefix sums that will have the same size as array A. Here an aside, it is sometimes preferable to have a prefix sums array of size A plus 1. That way we will avoid dealing with out of bounds when we subtract 1 from I. So as we saw with the animation, we start by setting the prefix sums of 0 to be equal to A of 0. Then each entry from 1 to the size of the array will simply be equal to the previous entry in the prefix sums array plus the actual value of the array at that index. And the answer for interval I and j will be equal to the prefix sums at j if I is equal to 0. Otherwise, it will be equal to the prefix sums at j minus the prefix sums at I minus 1. If our array was one index, we wouldn't have to perform this check since I minus 1 will not become negative. So as we said, the pre-computing took us all of n, and each query can be answered in O(1) since it only requires one operation. And if we had to answer Q queries, the total complexity for all queries would be O of Q. For a total complexity of n plus Q, which is way better than the complexity we had in the previous approach, which was n times q. So this prefix sums technique is great, but since we only saw it in this context of a sum over range, we gotta ask ourselves, can we apply this technique to solve different problems? And the answer is yes, we can. In fact, we can also find the product of a range. Addition and multiplication act the same way in this context. So this pi symbol here replaces the sigma symbol in addition, and it stands for the product of an from n equals I to j. And this will be equal to the product from 0 to j of an divided by the product from 0 to I minus 1 of an. And you can make sense of this relationship by linking addition to multiplication and subtraction to division. Since they act the same way, we could apply our previous technique to find the product of a range. The code for this application is pretty much the same. The only difference is that for pre-computing the prefix product this time, we use multiplication instead of addition, and the answer, if I is different from 0, would be equal to the prefix product of j divided by the prefix product at I minus 1. Of course, you gotta be cautious when using this trick in the context of products, because as you know, products grow really fast. So you need to watch out for overflow issues. You also need to watch out for entries that are equal to 0, because the product after that entry will always be equal to 0 and you cannot divide by it. To avoid both these two issues, you might be required to calculate the range product modulo some prime number. And in that context, the pre-computing would be pretty much the same. You would just need to calculate the product modulo that prime number. And for the answer, instead of dividing by the prefix product at I minus 1, you would multiply by the prefix product at I minus 1 raised to the prime modulo minus 2, since that value represents the modular inverse of the prefix product at I minus 1. Another application is that of finding the XOR of a range. So if you don't know, the XOR is a binary operation that is equal to 1 if the two bits are different, otherwise it is equal to 0. So 1 XOR 1 would be equal to 0 because 1 is equal to 1, and 1 XOR 0 would be equal to 1. And if we have a number XOR another number, we go bit by bit, and then we check if the two bits are equal, then the answer would be equal to 0, otherwise it would be equal to 1. In this case, we leverage the fact that any value XOR itself would be equal to 0, because all bits in the two numbers will be identical, so their XOR will be simply 0. This property allows us to write the following equation. So the XOR of all values from I to j would be equal to the XOR of all values from 0 to j of a of n XOR all the values from 0 to I minus 1 of a of n. So all the values between 0 and I minus 1 will be XORed with the values between 0 and I minus 1 from the first sum, and they will simply cancel out to leave us with only those values between I and j. So in terms of code, it is pretty much identical to the two previous ones. For the construction, we proceed the same way. We set the prefix XOR of 0 to be equal to a of 0. Then each subsequent entry of the prefix XOR array would be equal to the previous entry, XOR the value of the array at idx, and for the answer, it would be equal to the prefix XOR at j if I is equal to 0, otherwise it would be equal to the prefix XOR at j, XOR the prefix XOR at I minus 1. Wow, this technique turned out to be pretty powerful. So now we can do addition, multiplication, XOR. What about the max? Can we find the max of a range using this technique? And the answer is no. Consider this array now. We will try to construct a prefix max if you may. We will start by 12, and then each time we will take the max of the prefix max with the values of the array. So we get 12, 12 again, 12. Basically, we will get 12 for all the entries in the array. And as you can see, the prefix max array we constructed is oblivious of the values in the original array. So for example, at index 3 of the original array, there was a 1. There could have been a 7 there. It wouldn't have mattered. We would have gotten the same array. So constructing the prefix max this way loses data, and it makes it impossible to retrieve the original array. So unfortunately, we cannot apply the prefix sum trick to calculate the maximum value of a range. So we just encountered our first problem. As we saw, this technique does not work with all associative binary operations. It does not work with the max, the min, the GCD, the LCM, to name a few. And there is actually a second problem that we did not consider too much because we did not claim we could solve it, and that is of updates. So this technique does not allow for updates. What I mean by this is that the array we are given cannot be changed. And this means that I cannot change a value in the array without reconstructing the whole prefix sum. And if I have to do that frequently, it will cost me O of n each time I want to reconstruct my array. And this is not efficient. So to sum up, we need a data structure that can answer range queries in sublinear time. This means it has to answer queries either in O of 1 or O of log n. Taking O of n is too much and would be inefficient. Second, it should allow for efficient updates. And finally, this data structure should not require too much extra space. You've guessed it. The data structure I'm talking about is the segment tree, and it will allow us to do all these things. So stay tuned, see you in the next video to get the intuition behind segment trees. Thank you for watching, see you next time, bye bye.